Alright, so in this experiment, historically students have had a little bit of trouble making the plots for the derivatives. So I wanted to go through and show you how to do that. It's a pretty simple process, but it might be confusing if you've not seen it. So let's talk about that. So the first thing you need to do is open up Excel, such as what we've got here. And I've actually already started our spreadsheet. Let me explain what this is before we get rolling. I've got two columns, A and B. Column A is the volume added with your burette in milliliters. Column B is the observed pH. So this is basically your raw data. Now I've just made up these numbers here through about 35 milliliters and associated pHs. You of course would measure these and enter them into your Excel spreadsheet. That would be your first challenge. And of course label the columns so you know what everything is. It's important to keep track of all your data. Now the second thing that you might want to do once you've accomplished the data entry into the spreadsheet is select all of your data and add a scatter plot up here. I'll just do this marked scatter in my version of Excel. And what that does is it's going to make us a data point or a data plot. It's a scatter XY plot in which every point that you've recorded actually now shows up. So it looks a little bit like a titration curve. Okay, yours will look different because I actually just made up these points, but you get the idea. Now I'm going to delete this series one bit, and actually probably to save time, it's probably best to go to this quick layout. I like to use this one, even though it adds this linear fit that we don't need. I can just easily delete that. And what's nice about this is it gives me my axis titles really fast, my labels, so I can come in, boldface it, increase the font so everybody can read that. I like to use 18-point font a lot in the charts that I make. When you're making your charts and your plots, you definitely, for presentation, you definitely want to make sure that your font is bold and big enough for people to read. Oftentimes it said 18-point font. It's good. Now we also want to label our axes. So on my x-axis it's volume titrant added in milliliter units. That's what we plot down there. Make sure my caps are good. Now over here on the y-axis, I've got something different plotted. I've got my pH. I double-clicked, unfortunately, so gotta clear that. But now I'll come back, label pH, and make my font big enough for everybody to read. Looks like it is now. That looks a little bit like a titration curve, okay? I like to have these X and Y tick marks and actual grid lines. It allows the reader to pretty quickly figure out, where the data point's located, both the X and the Y coordinate. Another thing to kind of stress when you're making these plots, not only you want your axes labels and associated units, but it's also a really nice thing to make sure that the data points show up on your plot, and also the aspect ratio of your plot is approximately 1:1, which means it appears square. So this XY coordinate system is square. What you don't want to do generally is something like this, okay? Where your X dimension is 2 or 3 times the width of your Y. I guess it looks kind of nice to the eye, but you're really kind of stretching that X dimension. And usually we're looking for linear trends and things of the sort. So it's kind of nice, I think, when there's a 1:1 aspect ratio, your plots appear square when you're making them. So just some minor things there, just about making plots. Okay, so we've got our titration curve. That's actually the very first plot that we want to make for the titration. So I'm just going to kind of set that here. We can print that out later as necessary and include it in our report. But of course, the harder part is to make the plots for the first and the second derivative. So let's dive into that now that we've seen how to make this simple graph, okay? So we're going to have to generate another X and Y data series, okay? We'll call them X and Y for right now. Now, and this is going to be for the first derivative plot, okay? Now, when we think about plotting the first derivative, we have to come up with a pretty good mental picture of what it is we're plotting. And again, what that's going to be is the slope along this curve at every point or every volume. Okay, we want to measure the slope of this line along the curve at every volume of titrant added, and that's really what we want to plot. Okay, So how are we going to do that? Well, let's start with our y, because that's sometimes the most confusing. Well, what is the y? Well, that's going to be the slope at every point along this curve, the delta y over delta x, or the change in pH or change in volume. So that's basically the first derivative, right? So it's dpH per dvol. We'll call it that just for simplicity, I suppose, and make that bold-faced and perhaps a little bit bigger so everybody can read it. Now, mathematically, how do we calculate that? Well, what we're going to do is we're going to use this data over here to compute both the change in pH and the change in volume, and we'll do the division by entering an equation or a formula, and Excel is going to basically do the math for us. It's going to be a little bit easy, okay? Now you have to remember, when you're computing this derivative, you're always computing the change between two adjacent points, okay? So here, that's this point in cell B3, which is pH 2, and then the previous, okay? So I'm actually not going to compute any value for this first box because I don't have anything to compare this to previously. But I can compute a change in pH for the second point by entering a formula. And this formula is going to be equals, parentheses, B3. That's a cell address, right? B3 lights up nicely so you can see it. And I'm going to subtract B2. So what I'm doing here is I'm doing the value in B3 minus the value in B2. That's 2 minus 1.95. So of course the answer is going to be 0.05. Excel is going to calculate that for us. But notice that I type in the formula here with the cell addresses. The reason for that is going to become apparent in a second, because I'm going to copy and paste this, and it's going to make my life easier. So you really want to type in those cell addresses, not the actual numbers. Okay, that's going to be important. I'll show you that in a second. Now once I compute my change in my y, which is this minus this between the points, I'm going to divide that by my change in x. Because remember, my derivative is delta pH divided by delta volume. Okay, the slope at the point H point along the curve. Now how am I going to do that? Well, I'm going to enter a formula in much the same way. But now my volumes are in column A over here. So I'm going to need to do A3 minus cell A2 parentheses. Everybody see that? Now if I click on that, notice what does Excel do? It computes the result for me as a number. Now does that result make sense? I think it does, right? Because just if we double check the math in our head, if we do this cell minus this cell, it's 0.05. And if I divide that by 1 minus 0, that's dividing by 1. So 0.05 is our result, right? So that makes a lot of sense. Now the beauty of entering the formula in, so you have to do equals and then the cells and the mathematics, okay? But the beauty of entering that in is I can essentially copy and paste that down the column all the way through my data series. And boy, that makes my life a lot easier. Because notice I didn't have to think about the result for any of the other boxes, right? I just copied and pasted it. And notice up here, what it does is Excel's kind of smart, and it of course updates for the next row down. So the value right here in cell D8 is this value in B8 minus its previous measurement, B7. So this difference divided by this difference, okay? So it's really convenient, a very convenient way to compute these derivatives. And we've got a lot of different numbers for all the points along our curve. All right, now that's our y values. This is a great first start here for our first derivative. But we're still not done. We got a little bit of a problem because we don't have any corresponding x values to use yet. Now x values, the ones down here of course is going to be the volume. Now what volumes do we want to use? We have a series of volumes for volume added here, but what do we want to use for this derivative plot? So I'll call this the first derivative volume. We have to think about that a little bit, which volumes to use. Now, what makes sense? Well, I think what makes the most sense to me is if we consider the volumes over here and we use the average or the midpoint between these two, okay? So in this particular case, this value right here is really kind of associated with the change between these 2 points. And of course the midpoint there would be 0.5 milliliter, okay? It's essentially the average of these two. So I think that's what we're going to do. So to help us with that, rather than have to type in, 2.5, 3.5, all the way down, okay, why don't we just do another formula? So when you enter a formula in Excel, you always start with equal, and you type in what you want to compute. So here, average is a built-in function in Excel, fortunately. So I type in average equals average, parentheses, and then you got to define the range for Excel, what you want to compute the average of, which is going to be these two boxes right here. I hit enter, and see my average is 1.5. Sure enough, I can paste that, copy and paste all the way down my column. Oops, didn't work that time though. I can copy and paste that all the way down my column. And this is going to save me, again, a tremendous amount of time, because now I've got all my values, didn't have to think about it. And what I can do now is come in, highlight this data by selecting it, go to Insert, Chart, Scatter, mark to Scatter, and sure enough, there is my first derivative plot. Again, I like to use the quick format feature, it just saves a little bit of time. I can move this plot over under the other one now. Again, square it up nicely. Before I move on too far, I can think about formatting everything with proper titles. For now, I'll just call this first derivative dph dv for volume. Looks like maybe I have a cap over here that doesn't need to be there, so let me clean that up. Another thing I can clean up is right here. Notice this D. If I want to, I can make that a Greek symbol for delta. Computer, take a second to think about that, but you go back to home and then you choose the font face that you want to use. And if you go all the way through the close to the end, oops, there's one for symbol font. If you click on symbol font, that'll actually use symbols now. Now I made it a capital D instead of a lowercase d. You could really use either one. Either one is somewhat typical. But the capital D is that nice little triangle that you're so familiar with from your chemistry classes. So again, I'll change the other D to the symbol font, and again, I'll insert the capital instead of the lowercase. So same sort of stuff. Just come in, clean this up, make it look nice and presentable. I'm kind of spending some time showing you this because it really is an important thing. When you start thinking about getting out of the university and start making your plots for your professional career, whether that be graduate school, preparation of reports for your employer. You want to make sure that you do a good job with your data plots. People kind of expect that. And it certainly reflects well upon you. Alright, so I've been successful in preparing my XY plot here for my first derivative based upon the data shown up here. And as we might expect, if I measured the slope along each point here, the slope would be, some positive number here. But then once we get to this region right here, boy, that slope's really going to take off, isn't it? Because that's where we've reached our endpoint, and that certainly is reflected here in my first derivative plot. And of course, the first derivative goes through a maximum right here, about 25 milliliters. And that is at the endpoint. It corresponds to the endpoint. So here, that the value for the derivatives was just a little bit over 45, about 25 milliliters. Okay, so that's our first derivative plot. Simple enough, right? So you saw how to do that. Now, what about our second derivative? Now, when we say second derivative, we're referring to the second derivative of that original data, right? the original titration data that we collected in column A and B. It just so happens, maybe you've figured this out already, that to take the second derivative, a pretty practical approach would be just to take the first derivative of this data in C and D. Right? This is our first derivative, and we can take the derivative of that and get our second derivative information. So that's the approach that I'm going to advocate here, okay? So again, we skip the first one because we don't have a comparison point. We come in here and we can enter a formula. This is going to be our well, I messed up now, so let me clear that. Let me label this. It'll be a second derivative change column and our second derivative volume column again. Okay, so skip the first one, come here. I can do equals D4 minus D3. And then I'm going to divide that by the change in my x, which is C4 minus C3. It's the same sort of stuff, right? Just computing my delta y divided by delta x. I get that value. Over here now, I want to compute my average volume again. So I just come in, compute my average. And now I've got that point and that point. I can copy and paste. And we get a bunch of numbers. And now let's see what we can do with these numbers, okay? We can select them and plot them. Chart, scatter plot, mark scatter. Place it right here. Use the linear fit. I don't really want that again. I just choose that chart because it's kind of convenient. You know, it has a lot of the features that I like to see in the way it's formatted. So this is our second derivative. Clean things up here, make it the 18-point font. Oops. Down here will be our volume. Alright, that looks pretty good, I suppose, for formatting. Oh, except for these numbers. We need to do something about that. Make them bold usually, make them 18 font. Alright. Now it's a little bit hard to see, and perhaps I may want to change the things. These are, or change the way these are plotted here. So I think I would need to go to format data series, if I remember correctly, marker line, or just line, and I'm going to put in a black line here. Oh, but I just did that between 2 points, so let me cancel that. I need to select the whole data series. Line, black line. It's not really wanting me do that first. Oh, maybe it's okay, it's too close together. That could be why. So the reason why I did that was to try to stress what we're looking at here. I'm going to change the scale instead here to really key in on what we're trying to see. Oops, that's the maximum. So I'm going to zoom in between 20 and 30 on this plot. And that's a little bit better. Okay, you can kind of see it. Yeah, in fact, there is a line in there now. So this is 20 milliliters, 30 milliliters. I just kind of zoomed in for clarity. Now notice here that the second derivative is very small, close to 0. goes through a maximum, crashes back down through a minimum, and then back close to 0. This is easily explainable because remember what we're doing is taking the derivative of this plot, which is flat, and then shows a peak back down to being flat. So clearly the slope here is very small, very small, very small. It goes through a maximum, crashes back down, and then very small. And that's what we see in our second derivative plot. It goes through a maximum, right where that equivalence point is, crashes back down through 0, and then it comes and levels back off again, okay? Goes through a very large negative slope here on the downside of that peak. The upside is the very positive slope. The downside of this peak is where we crash back through the negative. So we like to say that the 0 crossing point in the second derivative plot is where our endpoint is. So that's how we use the second derivative. So on the second derivative, we crash through 0, and that 0 crossing point, that point of inflection of the first derivative curve, that's our endpoint. For the first derivative analysis, we look for the peak. And of course, for the actual titration data, that corresponds to the steepest point on the curve. So this is how we can use our graphical methods to determine endpoints of titrations. Now, in this experiment, you need to make this spreadsheet and turn in these plots for your titration. You need one of each of these, one second derivative, one first derivative, and one data plot for each titration that you carry out. So you do a weak acid, a strong acid, and a diprotic acid. You're going to need to turn in 9 of these plots, 3 for each of the titrations. And that's what the expectation is for your data for this lab. Thanks. I hope this was helpful.